Hello everyone, welcome back to PMAC1140. In this video, I will be introducing one of the last two functions in college algebra. The function is called exponential function. And in this video, we also discuss the domain of exponential function. We will go through some application of exponential function, how we use exponential function to model word problem. Okay, so let's get started. So I'm going to put the topic right over here. Exponential function. Okay, so in the first part, let's talk about what exponential function look like. Okay, so in the first part, let's talk about the definition of exponential function. Okay, the exponential function will be something as follow: f of x equal to a b raised to the x, okay, minus h plus k. Okay. All right, let's try to explain and interpret each letter right over here. The a value here, we call that initial value. Initial value. I'm sorry for the background, okay? And I have very bad allergy, so again, I'm sorry for that. The initial value, which is when you replace x with 0, okay? Then you have a value, okay? Replace x with something, that is called initial value. And the b value here, we call that exponential factor. And the h and k, the initial value here could be a positive, or negative, okay? Because if it is positive, then it could be above the x-axis, so we already know. And the transformation concept, if it is negative, could be flip it over the x-axis, so it could be positive or negative value. But the b value here, okay, the b value here, it must be greater than 0, okay, must be greater than 0, so b must be greater than 0, okay, because if it is less than 0, we don't have, if b is less than 0, we don't have the function. So if b equals 0, then function does not exist. Okay, and the h and k over here is nothing but transformation. The h and k over here, it tells you how many is going to the right and how many going up or down. This is how many going to the right, left, and the k just tell you how many going up and down. So this is the transformation we already learned, h and k. So if h and k equals 0, then what happened? If h and k equals 0, then my function become f of x a b to the x only, right? A b to the x only. I mean, if it doesn't have any unit moving to the right or any unit to the left or up or down, then my function will become f(x) equal to a b to the x. And if b is greater than 1, okay, if b greater than 1, then the function f(x) is exponential. exponential growth function. Okay, exponential growth function. That is when b is greater than 1. If b is between 0 and 1, then is exponential decay function. What does it mean by grow and decay? Graphically, this is what it look like when b is greater than 1. If b is greater than 1, the exponential function look like this. Here you go. So that is the case when b is greater than 1. And if b is between 0 and 1, the exponential function look like this. So what do we see out of this graph? We see that the function of b is greater than 1, or the b greater than 1, where the function is increasing. And if it is between 0 and 1, the function is decreasing. But it decreasing, but it's increasing, but it never cross the x-axis. It's decreasing, but it's never cross axis. So the x-axis here, the x-axis is the horizontal asymptote. Okay, that's the x-axis. Okay. Asymptote. Okay, x-axis. It means that the graph here, it never crosses the x-axis. Okay, remember that it never crosses. Okay, this is x-axis here, this is y-axis here. It's x-axis. And another thing I want you to notice is that it never crosses it, so it cut the y-axis right here. So this point right here, the initial point, which is the initial value right there, initial point. Okay, so this is increasing and that is decreasing. Another information we can get out of this graph is that the domain is always from negative infinity to positive infinity. The domain here is also negative infinity to positive infinity. If the function is not transformed up or down, okay, then the range will go from 0 to positive infinity, right? Because it never crossed 0, so it's going up because of the range. Look at the y. So is the range here. It's all the way from 0 to positive infinity. Of course, it's not always like that, because if the horizontal asymptote is moving, it means that we have the k value here instead of having h and k equal 0. If we have a k value that is different from 0, then the function will be moving up or moving down. Okay. Now let me give you before giving you an example. So I know that if b is greater than 1, the function is a growth function, right? And the b value for the growth function, the b value, we call that the growth factor. Okay, just add that. So this is growth factor. Okay, for the b is greater than 1, and this is decay factor for the b between 0 and 1. Now, let me give you the example now. Okay. Example number 1. Let me give you something simple first. So f of x equal to 3, 4 to the x. There you go. So over here, the function, the b is greater than 1, right? So it could be, if we go ahead and do the sketch, it's going to be something like that, right? And the a is greater than 0, so it would be above the x-axis. Okay. Or the function could be this: 0.75 raised to the x. Okay, so you see that 0.75 between 0 and 1, so it will be something like this. It's going down like that, right? Or we can write this as a fraction like that. same thing. So this is the b value. This is a decay factor. This is a growth factor. That means greater than 1. And this is between 0 and 1. So this is decay factor. So the scratch will be going down. Okay. Or example 2, if b is the e number. E number. What is the e number? You go ahead and put it into calculator. E number is about 2 point something. So if a is -2 and the b is an e number, okay, it work also because this is greater than 1. So it will be reflection will be reflected about the x-axis. So if we go ahead and sketch it, because it's negative over here. It's the reflection about the axis, so it will be mirror about the x-axis. Okay. Okay. If it doesn't have the negative, so it's going to be something like this. Let me go ahead and draw this sketch for you. So if it's just positive 2, okay, if it's just positive 2, then we know the function will be something like that. It will be 2 e to the x. Okay. Okay. 2 again is 2 point something. Let me go and check real quick for you. You put into calculator. Let's see. Do I have calculator over here? Is 2 point something. Oh, I don't know how to put it. I don't know how to put it into calculator here over here. Okay, hold on. The calculator quick over here. The number exactly 2.71. 2.71. Okay. 2.71. So that's why the e number, which is the growth factor right here, because it's greater than 1. That's why it's going to be increasing like that, and the e value, the x equal to this initial value is right here when it's positive, but because this is negative, so you're going to flip it over. So you're going to flip it over. There you go. So they become -2 e to the x. Okay. So if it negative, okay, if it's negative, you're gonna go will be reflected about the x-axis. Okay. So if you have calculator, it'll be very easy to see. Now let me give you something that has the transformation concept. We can apply there. Example 3. What if I have function like this? If x equal to what if I have 3 2 to the x minus 1 plus 4. So this is also exponential function. What does it mean over here? It means that we have to move up 4 unit and move into the right 1 unit. So usually I just sketch. Okay, do a quick sketch for you. So usually we just have this, right? Oops. Because this is 2, the growth factor, so this could be something like that, right? Okay, that is for 3 times 2 to the x. But right now we gotta move to the right. We move to the right 1 unit. So let me use a different color right here. So we move to the right 1 unit. So move to the right 1 unit. So it means this value move over here. So become this value. Okay, and this one move a little, and we gotta move up. We gotta move up 4 unit. 1, 1, 2. Oh, I don't have. Let me see. 1, 2. I just guess. Okay, 3, 4. Oh, look like it's not a good graph. I think I'm gonna go ahead and erase everything. Okay, and move a little bit over here for you to see. There you go. There you go. So usually we're gonna have something like that, huh? So we have something like this. Okay, now we're gonna move it to the right 1 unit. Okay, now we're gonna move up 1, 1. Okay, 2, 3, 4. There you go. Okay, it's just a sketch. Okay, just a sketch. So we're gonna have something like this. Okay, so the horizontal asymptote will be 1, 2, 3, 4. So my new horizontal asymptote will be this, right? And 0. Okay, 1, 2, 3. So right here. So my new function will be here. New horizontal will move 4 units, and my new function will be in orange. Will be something like this. There you go, something like that. Okay. Again, I just do a quick sketch. The sketch is just it's used to demonstrate the transformation. Okay. It's not a graph. I mean, we can do it more detail if you want it by just plugging a point, but I don't see the point we have to do that. I just want to show you, and it's for you to understand the h and k value over here. Okay. Okay. Now in the example number 4, I will show you how to write exponential function given information. Remember, back in the day we learned how to write linear function or linear equation of y equal to mx plus b, right? And now this is exponential function. Okay, because x is exponential function, we don't have slope anymore, we don't have b's, but we have something else. Okay, right? Exponential function. Okay, that goes through 2 points. The first point is -1, 8, and the second point is 1, 2. That's all. Alright, so in order to write exponential function, we need to write the formula now. So the formula is f of x equal to ab to the x, because they don't tell you about how many moving right, how many moving left, so we don't have h and k. Okay, we just have this. Okay, and we know that it's go through 2 points, so fx is the same as y. So all we have to do is just plug in a point in. So first point is 8. Okay, ab to the -1, and second point is 2, ab to the 1. Okay, and now we're going to solve for a and b. As long as we solve for a and b, we're done. Okay, so the b value here is different from the b value in the y equal to mx plus b. Okay, don't use y equal to mx plus b. This is not linear function, it's exponential function, so we have to use this. Okay, we don't have the slope, you see that? So we just need to solve for a and b. So how we solve for a and b? You can go ahead and rewrite this as a over b, because b to the -1 is actually 1 over b. Then this is the same as 2 equal ab, right? Because b to the 1 just b. Now what we have to do is we're gonna solve a in terms of b, so a will be ab. Then you're gonna plug a over here, so then 2a will be ab times b. Plug it in. Alright, plug it in. Replace the a over here with ab. So we have 2 b squared. So from here we have b squared equal to 1 4. Alright, if we go ahead and take a square root both sides, right? So usually we have plus and minus, right? 1 over 2. But because remember the condition, the b must be greater than 0. If b is equal to 0 or less than 0, oh, I forgot to add it. 0 or less than it, so I'm going to add it like that. Okay, if b is 0 or less than 0, then the function does not exist. In this case, you see that b equal negative 1 over 2. Okay, and if b is negative 1 over 2, which is less than 0, so we don't have a function. So it means that we just take okay, take b equal half. Okay, and if you take b equal to half, then my final answer will be f of x equal oh, we need to find a. Okay, so b a half, so it means you plug over here a times a half will be a equal 4. So my final function will be 4 half raised to the a. There you go. Okay, so this is the decay factor because it's between 0 and 1, and this decay factor is going to be, if we go ahead and sketch, it's going to be something like this. Just sketch, okay? It'll be something like that. And I don't know why it's kind of very hard to draw. So let me draw this carefully here. Sketch, okay? Sketch. It'll be decreasing like that. There you go. Okay. So this is x right here, and this is y. Alright. Alright. So let's see what else. So I give you, for example, I think that's good enough for all the case. It's just all okay. Sometimes we don't have the k, but we have the x. It works. Okay. What if I have something like example number 4, example number 5? What if my function is this? 2, 3, x plus 1. Okay, this is also work. Okay, we have move it to the left, but we don't have moving up or down. So this is also exponential function. So in this case, domain, right? The domain is still a negative infinity to positive. Okay, the same thing over here. The domain is negative infinity to positive, but the range is different, huh? The range over here is the range will be from 1, 2, 3, 4, from 4 to positive infinity, because we move up 4 units already. Okay, we move up 4 units, but the over here the domain is still the same, negative infinity, positive infinity, and the range is for the negative one. The range will be from negative infinity to 0, not included. Negative infinity to 0, not including 0. For this function, okay. For this function, okay. All right. So we already know what an exponential function look like. Now on the second part of the video, okay, I just want to talk about the application of an exponential function. How we're going to use exponential function to model word problem and to solve word problem. One of the application of exponential function is used to calculate the compound interest. What is compound interest? So maybe some of you already heard the term simple interest, right? When you have $100 you put in the bank and that bank pay you 1%, it means that every year you got 100, and every year you got 1% of that 100 will be, after the first you have 101, after the and second year you have 102. Okay, so the difference between that kind of interest and the compound interest is that the compound interest, you have the interest on interest, mean that the interest on interest must be applied. What I mean is that if you have 1% of $100, then after the first year, the second year will be 1% of 101, and so on. Okay, and the formula used to calculate compound interest is A equal to P times 1 plus R and raised to the NT. Okay, and the N over here could be different, depends on how many times you compound. So N could be 2 semi-annually, that means you compound twice per year, and annually means you count 1 per year, and monthly 12 times per year, and 4 quarterly, and daily mean 365. And the p-value over here tell you the principal, means the reasonable amount you put in the bank or you put into a certain investment, and the rate is the interest rate. So the rate is the interest rate. Okay, and I tell you how many times you compound. It is the amount of time you used that that investment, the amount of time you play with that investment. Okay, so the bigger the n value, the bigger the n value, okay, then the bigger the a value. The bigger the n, the bigger the a. It means that the more you compound, the more value you can receive, okay, from the original. Okay, now let's take a look at this one. So I have a problem. Hannah received inheritance, okay, of $20,000, and she decided to invest this money for 5 years in the certificate deposit. It is one of the investment, and this one pay 2.65% compound monthly. The first question is how much does she has to pay? Oh, how much does she have in the bank after 5 years? I mean, how much in the bank? I mean, it's like how much she accumulate after the first 5 years. Then the second question is if she invested into another investment, and but this one pay like more, the interest is much more, but compound quarterly. Okay, which option should be produced highest rate? And first is how long will it take for Hannah to 20,000 to grow to 150,000 if she invested at 5% annual interest compound semi-annually. So in the first question is very easy to answer. You just need to use this formula here, and it's 20,000 is the original, which is the B, and monthly mean n equal 12. You plug it in, it give you this much. Now for the second question is the compound quarterly. I mean, you see the quarterly n is equal 4, right? Usually if n is small, it means that you won't receive much compared to monthly, because monthly n is 12, so this one they pay you more than n equal 4. However, because the interest is pretty high, very high, now if I go ahead and plug it in, you see that you still making money, and you make more than the first type of investment, right? This is 25,000, and this is only 22,000, and you see the quarterly you plug n equal 4 over there. 4 times 5 equal 20. Now think about it. If the rate over here is not 5.19%, what if the rate is the same as the 2.62? Then I'm sure that part A will be with the first investment you will make more than the second one, which is for n equal 12 you will be making more money than n equal 4. But because the rate is very high, that's why for the compound quarterly it is more than compound monthly. Usually compound monthly is much better quarterly, because they're like you had a compound. It is compounded 12 times, and for quarterly this is compounded only 4 times, so it's 12 times is much better. So it means that if you compound it daily, this is the best. Okay, this is the best. Alright, so this one will be better in this case. Now, how long would it take for 120 to go with 250,000 is 5%? So compound semi-annually, so only n equal 2. So it's 150,000 is the last amount of money you have, and originally you have 20,000, and you plug it in, and you need to solve a t because I ask you how long you solve a t. So you calculate everything. Now you calculate this out. You divide both sides by 20,000. You divide both sides by 20,000. Then you calculate whatever inside the parentheses right here. And in order to solve for t, you need to know a very special key button on your calculator, TI-84, and you're gonna hit LN. LN is one of the key, the button on your calculator. You take LN both sides. I'm gonna explain later, maybe in the next video, what LN means. But at this time, you just need to hit LN of 7.5, which is on your calculator. Okay, you click and you hit LN of this. And ln of 7.15 give you this, and ln of 1.025 give you that, and you solve for t and you see that it gives 41 years. Think about it. You have 20,000, and in order to grow to 150,000, it requires 41 years. And this is, think about this, is a very ideal case already, which is 5%. Nowadays, I don't see any bank pay you 5% or any investment pay you 5%. So, and you see that even if they pay you 5%, it's 41 years to get to that money. That's a lot. That's a pretty long, very long time, right? You probably died by that time, you know. So think about that. For some poor people, right? I mean, $150,000 or $100,000 is a big amount of money. Of course, if you, some people really rich and $100,000 nothing. But I mean, if you do just regular job, and $150,000 is a lot of money. You know, it requires 41 years to get that much. Think about that. And this is an ideal case already. If the 1%, as we usually get paid by the bank, then maybe this is maybe almost 100 years, or maybe at least maybe 80 years. No way, right? No way to get it. So that's why I really love about the application of exponential function, because it tell you, it tell you, it help you understand how the life is working, right? The realities, okay, what is going on, you know, outside mathematics, right? You understand more how the bank's working. That's what it is. Okay, so that's the first example for the compound interest. There's another type of compound interest. We call it continuously compound interest, which is when, and just think about when n approach infinity. When n approach to infinity, then the formula, which is you compound infinitely many times. Okay, then the formula is this. Now I'm gonna use the same number so that you see that the continuously compound interest is a very it's the best case. I mean, it's a very ideal case. Think about it. Now, if you have 20,000, right, and you're gonna use this formula, you put 20,000 in, and for 5 years, and the same interest. Okay, you see that you make 22,799, and this is 20,796. So it's $3 more. Think about it, $3 more. I know for 5 years it's nothing, right? But I mean, because 2.62% compounds monthly is very ideal already, you know. So this is the most ideal case in which they even pay more, even though you see that it's not too much. It's only $3 more, but it's still it's no way, no place on earth pay you that much with that interest continuously compounded. You know, nobody pay you this, let alone this. All right. So there's another application of exponential function, but again, I mean, I don't think that we're gonna focus too much because there's so many applications. I don't think we can go through all of them. So I think I'm gonna just stop right here. Okay, I think I'm gonna just stop right here and I introduce just only 2 of them. Maybe how about we do this? Maybe we should do one more application, okay, about decay. Maybe we doing that. Okay. Yeah. So let's do that. Okay, let's do that. So exponential function can be also used to model exponential decay of radioactive substance. The mass of radioactive substance is decay exponentially. Okay, for example, something like this. So the application would be could be radioactive substance. Okay, decay. So I'm going to put a decay. Alright, so for example, I have this problem here. The half-life of carbon-14 is 5,730 years. Okay. Here. Find the exponential decay model of carbon-14. Okay, find the exponential decay model of carbon-14. Alright, so that's the question. So the formula we're going to use in this case will be P equal let's see, e to the negative. Okay, so we P, so the formula will be P equal P0 e to the negative KT. Okay. Alright. So P0 again is the initial amount. Okay. And T is the amount of time. So they give you this already. Okay, so our job is need to find K. So after you find K, which is decay factor, this is decay. This is decay rate right over here, right? Decay rate over here. So let's see how we're gonna do this one. Okay, so think about it. We have the formula A. The formula exponential formula a b to the x, right? A b to the x. So x in this case t, a in this case this. So the decay factor is the e to the negative k. K is the rate right there. K is the rate right there. Okay, the rate. All right. So So we can as long, because they give you the half-life of carbon is 5000. Half-life will mean p0 is p, so p will be p0 divided by 2, right? So we're going to use this formula. So we're going to go ahead and plug it in. So the new p, so I'm going to go ahead and box this formula for the k. So the p will be, in this case the p will be p0, p will be p0 over 2 because half-life. So my new equation will be p0 over 2 equal p0 e to the negative k 5730. Okay, so which is give you half e to the negative 5730k. So our job is to find k. So as long as we find k, okay, then we're done. As long as we find k, then we're done. K is nothing but this the k factor. The whole thing is the k factor. Okay, so let's see. So how are we gonna find k here? So again, we're gonna use the ln. So 1 over 2, which is 0.5. Okay, so we're gonna do ln of both sides. Again, I'm gonna explain what ln mean next time. Okay, so you have ln of 0.5. Okay, will be negative 693, and ln of this, which is ln of, if you take ln of e, will be throw it away, so you have left is 5730k. Okay, just go ahead and put ln of e. This is what you have left is 1. Okay, ln of e number, which is 1. Again, I'm going to explain to you why we have that later. Okay, but ln of e number is 1. Okay, I'm going to put over here ln of e number is 1. Okay, alright, so over here I'm going to solve for k. Okay, so your k will be divided by 5730. Oops, 16. So I'm going to divide by 5730. Oops. Yeah, I calculate wrong. Okay, divide by 5730, which is 1.209. Okay, k will be here, so it will be 1 negative 1.657. Let me see, I just calculate them right now. Okay, so we need negative 1.209, negative 1.209 raises to the negative 4. Alright, which is positive signs, so which is very small one, huh? So about 1.000129. Alright, so that's just the k. Okay, now as long as we got a k, okay, as long as we got a k, let's see if I calculate them right or not. Something not right. ln 0.5 divided by 5703. Okay, negative. I just want to calculate a 5703. Oh, but they couldn't calculate it. ln 5 by negative 5703. Alright. Yep, so that's your k. That's your k. Alright, that's pretty small one, but Yep, I think that's what it is. So my equation will be P. My final answer, my model will be P0. Will be P0 here, e to the negative 1.0001209 t. There you go. All right, the rate. Okay. So it is about only 1.01209%. That is the rate. It's very small rate. So the case is around only 1.01209%. It's very small. Yep. Well, it makes sense because it took a long time to decay. Take a long time. The rate is too slow, it take a long time to decay this substance right here. All right. Let's see what else. Of course, there's more application. Let me see if we have anything else here. We can do another one. Okay. Right. Okay. This I think there's a kind of very interesting problem here. It can, because the exponential function can be used to model the population grow also. Okay. So we can use that exponential growth. We can use exponential function to model population growth. So the formula kind of the same thing, but instead of negative, we're gonna have positive. Kind of the same. Let me see. I can give you that problem. For is the population growth. Okay, and we also use that formula. So we have P equal P0 e to the kt, but instead of negative, we have positive. Okay, for example, I have this problem. As of 2010, the population of India estimate is 1.17 billion people, and it representing 70% of the world population. Only China has a larger population. In 2001, the population of India estimate is 1.03 billion. Okay. At a continuous growth rate, the demographer expect a population to surpass population of China by 2030. When China is projected to have population of 1.47 billion people, write natural exponential function that model the population of India. Alright, I think that's a very good example. Okay. Alright, so as of, we'll go ahead and write out the problem. As of 2010, population of India was estimated at 1.17 billion people. Okay, just go ahead, write them down. Okay, and this is represents 17% of the world population. Actually, that information is not necessary. But in 2001, the population again of India is only 1. Was estimated at 1.03 billion people. Okay, right. At a continuous growth rate, of 1.37% annually. Okay. They say that it would this rate, the population of India will surpass the population of China by 2030. Okay, when China is projected to have population of 1.47 people. Question A. Okay. Write an exponential model. Okay, write exponential model representing the population of India. Population of India. Alright, so let's see how we do this. Let's do one by one, okay? So where T is the number of years after 2001, T number of years, T is the number of year after 2001. Alright. So we have, okay, so we need to find we know the R already, right? We know the initial value is this, which is so we can write a P equal to 1.03 e to the rate is it? Okay, will be 0.137 t. There you go, right? Yes, let's see, it's the same as last time. It's the same as last time. Okay, we got K. You see, so which is a very small percentage, and they give you the percentage. Okay, so this one we had to find K over here. They just want you to write a model, and they give you the percentage. Okay, so that part A. Part B is find and interpret P of phi. Find and interpret P of phi. That's easy. So this P of phi mean after 5 years. It mean 2006. So P of phi mean in 2006 after 5 years. The population P of phi mean find the population after in 2000. So P of phi will be equal to 1.03 e to 0.10137 times phi. Okay, which is give you around 1.1 billion. Alright, so in 2006 is around 1.1 billion. Okay. Now use the model to predict the population in 2030. Use model to predict population in 2030, which is how many years? Yeah, it is 29 years, right? 29 years after 2001, right? Okay, so basically, so you're gonna calculate P29. Okay, P29. No, sorry. We need to find PX after 29 years. So you're gonna do P29. Yes, P29. Yeah, P29 1.03. E to the 00137. 29. Okay. Alright, so around 1.54 billion. Okay, so that is the population in 2030. And okay, so that, I think that's what it is. Okay, this is so these two examples here, so that you can understand the decay and the growth. Okay, if the decay is minus, if the growth is the positive. Okay. Of course, there's we can use a different way to represent exponential function. Can be written in another form to represent the decay also, because it can be used like a equal 1 minus r raised to the t. Instead of plus, could be 1 minus r. You know, could be like that too. But that is for the not a decay, but for the exponential decrease. It could be like that. Okay, it's not exponential growth. Exponential is 1 plus r raised to the t, right? But if it's exponential decrease, then it could be 1 minus r. Okay, let me do that one, that problem for you. Okay. Okay, so for number 5, we can use exponential function to represent the value decrease. So I'm going to put over here value decrease problem. Okay, for example, I have something like this, and we're going to use this formula. Let me write up. So we're going to use A equal P0 1 minus r raised to the t. So if it is grow, if it increase, then will be 1 plus, right? So remember the will be remember the compound one is the increased value, right? But the decreased value will be this. Okay. So this so I think I'm going to use different color. So it will be A equal P0 1 minus r raised to the t. There you go. Alright, so I had a problem like this. I have Chris bought a new car. And this car value $20,000 for $20,000, but the value decrease exponentially. Okay, decrease exponentially at the rate 8% per year. There you go. Remember that, per year. Okay, per year, just every year. Question is, what is value of the car after 5 years? Okay, alright, so we're going to use this formula. So we initial is this. We want to find A. So it will be 20,000 as initial value, and 1 minus 0.08 raised to the 5th power. Okay, So if we go ahead and calculate this out, 102 raised to the fifth power, which is only $13,181. Okay, dollars, $13,181. So you see that he actually after 5 years he lose around like 700 after 5 years. Okay, all right. So that you see that we can use exponential function to model the value decrease, or the value increase is easy already. For the this is the bank. Okay, that's for the bank. Okay. All right. Let's see. Of course, we have more. We have a different way of writing exponential model. Or we can do like this. This is also related to the population, growth population. So this is also grow population grow. Okay, this is continuously grow. Okay, continuously grow. Okay, how about this type of growth? Just a regular growth. Let's see. Population. Okay, this is also population growth. I think I'm going to put over here continuously population growth. Continuous population growth, so that because continuous it's like remember the continuous compound interest. Okay, so I'm gonna add a little bit over here to change this a little bit. Continuous continuous population population growth. Okay, and this is just population growth, regular one. It's not continuous. Okay, it's not continuous. All right, I have a problem with it. Oh, we're gonna use again for this one. We're gonna use just the same thing. We're gonna use something like this. Okay, we're gonna do something like this because I mean this is decrease, but this is grow. It's an increase. So instead of minus, we're gonna have plus. So we have a P0 1 plus to the T. Okay. Alright, so I have a problem like this. So in 1910, tiger population is 100,000. Okay. Let me see. 910. Okay. Population. Okay, I think it's not tiger. Let's change it later. Population in a town. In a town is 100,000 people, and the population in okay population increase at a rate of 30.4% yearly or annually. Okay. from 1990 to 2010. Okay. Okay. So part A. Let's PT represent the population model, represent population in the town. Okay, in the town. After 1910. Okay. Write the exponential function that model the increase. Right, exponential model. Alright, so we're going to use that formula. So we're going to have P of T equal to 100,000. Okay. 1 plus 3%, 3.4% T, which is raised to the T. So the model will be 100,000. Okay. 3.4%. So 1 plus 0.00034 raised to the T will be 100,000. 1.034 raised to the T. Here you go. That is the model. Okay. So now we want to use that model to estimate how many people there were in 1915. Use that model to estimate population in 1915. So 1915 and 1910 will be just 5 years, right? So we do P5 with 100,000, 1.034 raised to the 5th power, right? So you go ahead and calculate it. 1.034 raised to the 5th power, and you multiply by 100,000. So you have 190 people. That's the population of that time in 1915. Okay. Yep. Let's see. What else? Anything else we want to find? Yep, I think that's all. Okay. I think that's good enough. Population. We can add them up so we can find how long it takes. How long does it take to reach population of how about 2010? How about 2000? How is it? How long is it? It took to reach population of maybe 500,000. Alright, so let's see. It means that we plug 500,000 in, right? It's equal originally 100,000, then 1.034 4 raised to the t, so we need to find t because it's how long. So we divide with 700, so give you 5 equal 1.034 t. Again, we have to use ln in this case. We're gonna do ln 5 and ln of 1.034 raised to the t. So we're gonna calculate both of them. So ln 5, so it will be 1.609, and ln of 1.034 will be 0.0334 t. And now we can solve for t. So t will be 1.609. You divide 1.00334. Divide that, which is give you 48 years. 48 years. Alright, 48 years, guys. So which is 48 years. Then the town reached population of 500,000 people. So 48 years after 1910. So 1910 plus 48, which is 1958. Okay, so it means in 1958, the population is 500,000. Alright. Okay. Alright, so I think I'm gonna stop the lecture right over here. It's an hour lecture, more than that. So please, if watch it carefully. If you guys have any question, do not hesitate to send me the message. Okay, and I'll see you next time on the new concept. Bye bye.